Two more problems, starting Ex2D question 12. This one's a pretty weird problem. Let's have a look. So, find the side length of the largest cube. Okay, so when we say the largest cube, this really means of the cube with the largest volume. Okay, so as the diagram suggests, we'll let the length of the cube, or length of the side of the cube, be x. Okay, and let's let the volume be capital V. So let's see if I can write an equation for the volume. V equals length times width times height. They're all x. It's a cube. So the volume is x cubed. And then this other piece of information, can't really write any sort of relationship for it. I know that if I do some 3D trigonometry, the fact that it fits into a sphere of diameter 24 centimeters cubed, diameter 24 centimeters, that means that the length of this diagonal is 24 centimeters. I might just do this formally. So I've got a cube here. Put some hidden detail in behind it. Okay, I'm going to label this thing. You've done these questions previously, but just for those that haven't seen it before, I want to find the distance from C to F. Okay, but I'm first going to have to find, I can't find C to F directly. I know all of these distances are x. First I'm going to find the distance from C to H. So if I draw a triangle on the ground, I can have triangle CDH. These both are x's. Okay, and I know this distance CH will be, if I square it, since it's the hypotenuse, will be x squared plus x squared, or CH will be the square root of 2x squared. Okay, so I've found CH. Now I can find CF. Okay, in this scenario, I'm going to use this triangle that has the diagonal on the base, this height, and then that big diagonal that I'm after. Okay, and that's a right angle triangle. So I'll draw what that triangle looks like from a side view. CFH. This distance is x, this distance is the square root of 2x squared. I'm trying to find CF. I should be able to do this. CF squared, should put CF squared, all of these in brackets, is square root of 2x squared, so I'll square this, plus x squared. So CF all squared, squared and square root cancel each other out, so we've got 2x squared plus x squared, or CF squared is 3x squared, or we can find CF as the square root of 3x squared. Okay, so what have I done by finding all this? I know that in terms of x, okay, I know that 24 centimeters is the square root of 3x squared. Okay, that's the restriction placed on x. Yeah, it's the biggest that it can be. So I can solve this for x now, so square both sides. 24 squared equals 3x squared. And I can find x as square root of 24 squared over 3. Okay, that's the biggest value that x can take. Okay, whatever this is. Just quickly calculate it. And it should be square root of 192. Alright, I'll just put in square root of 192. Okay, so this question's weird because we're not really using optimization at all. This volume formula, x cubed, pretty much just looks like this. If I was to optimize v equals x cubed, I'd find one turning point and it'd be this point of inflection at the origin. So there's going to be no minimums and maximums like along this line. So all I'm really going to do is substitute in x equals the square root of 192 to find the maximum volume, okay, because that's where it'll be. Okay, remember, whenever you find maximums or minimums, at the end of the problem you should see is there any natural domain, and then test the endpoints of the domain as well. So from here we'll sub in x equals square root 192 into v equals x cubed, and hopefully there we get the right answer. Okay, but yeah, again, we haven't really used optimization. We've just used the fact that we need to check these endpoints whenever we do an optimization problem. Question 13 is probably a bit overwhelming when you look at it in the first instance. I've got a cylinder of cheese to be removed from a spherical piece of cheese with radius 8 centimeters. What's the maximum volume of the cylinder of cheese? I've never seen spherical cheese before, but let's just assume that it's possible. Alright, this is my radius r of my cylinder of cheese, and this is my height of my cheese. So I'll just define those two variables. Let r be the radius, let h be the height. We need to find the maximum volume. Maximum volume. Let v be the volume. Okay, so I can make a formula for volume of a sphere. Volume equals pi r squared h. We should be good at that by now. And now I just want to find some relationship between r and h. Okay, the way I'm going to find this relationship is by looking at my diagram and recognizing that because there's symmetry, that is going to be the diameter of the sphere. Okay, this bold thing that I've drawn is 16 centimeters, and we can form a right angle triangle there to find the relationship between the two variables. So I've got this triangle that has 16 centimeters, has h here, and has 2r down here. I can use Pythagoras, since there's a right angle, okay, it's a right cylinder, to write this relationship. H squared plus 2r squared equals 16. Okay, from here I'm going to rearrange for one of these and sub it in either to r or to h. In this scenario I'm going to choose to rearrange for r. Even though it looks a little bit harder, hopefully it'll help me out at the end. Okay, so I can write this as h squared plus 4r squared equals 16. Okay, I'll get the h squared by itself. and then divide by 4. So 16 minus h squared all over 4, and then take the square root of this, 16 minus h squared all over 4. Okay, so I'm going to substitute this into my volume formula. So I'm going to sub r equals square root of 16 minus h squared over 4 into v equals pi r squared h. Okay, I'll do that now. V equals pi times, I'm going to be squaring this thing that I'm going to write in brackets, 16 minus h squared on 4, okay, times h. So hopefully you can see why I chose to rearrange for r, because squared and square root in here are going to cancel each other out. I'll have 16 minus h squared on 4 times h, and then before I differentiate I can put everything along the top line, do some expansion, make it look nice. So I'm timesing by pi and timesing by h, so pi h 16 minus h squared all over 4, and I'll just do this expansion on the top line. So 16 pi h minus pi h cubed all over 4. Okay, and then from here we can split this into two individual terms so that we can differentiate. So 16 pi h all over 4 minus pi h cubed over 4. Okay, differentiate that. Find the height that gives you the maximum volume, and then you can use this formula to find the radius that will give you the maximum volume.